All right. Hello, everyone, and thank you for being here. On behalf of the Environmental Finance Center Network, welcome to today's virtual training, Water Quality in the Distribution System. This is part one of a two-part virtual workshop. My name is Kristen Crew from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics, and then we can go ahead and get started. During the training today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. GoToWebinar has recently gone through an update, and you can now add live captions, raise your hand, or react using emojis. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This training has been approved for 4.5 hours of drinking water continuing education credit in Ohio and Wisconsin, as well as 4 hours of drinking water continuing education credit in Michigan and Indiana. All attendees will also receive a certificate of attendance for their personal record. To receive credits or a certificate for the session, you must attend for the entire session and register and attend individually using your real name and unique email address. I will also say that if you're joining us from Ohio, be sure to keep this tab as your main tab because you do have a participation grade that will be analyzed by Ohio EPA. So make sure that you're paying attention, make sure that you're keeping this tab open and answering all of the poll questions that we send out so you can receive your credits. If you have questions or if you need assistance, please contact us at smallsystems@syr.edu. Now for a little bit about us, the Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which we'll be sharing shortly in the chat. And on that note, we can go ahead and get started. I would like to introduce our presenters for today, Daryl Gotham and Greg Pearson. They're both joining us from the Great Lakes Environmental Infrastructure Center. Welcome, Daryl and Greg. And Greg, I'll go ahead and pass it over to you.
Thank you, Kristen. Does the presentation appear to be up, Kristen?
Looks great, full screen.
Okay, well, welcome everyone. We sure appreciate you joining us today. We know it's just after all the holidays, and so we're glad that you're here today. Today's topic that we're going to be focusing on is water quality in the distribution system. And Kristen has already introduced us. And you see the symbol Ohio at the end of the title. That's because the state officials in Ohio chose this topic among all the topics that we offer, and it's a good topic. It covers a range of water quality aspects. Today we're going to be doing a short overview, and then we're going to focus on system flushing, corrosion control, and then cross connection control. And then the last hour, Daryl's going to take us through some basic math which is important for water quality management. And tomorrow, don't miss tomorrow, because we're going to be talking about disinfection and disinfection byproducts, sanitary surveys, sampling and monitoring as in relationship to compliance. So it's a well-rounded coverage of the topic today. And remember to stay engaged with us as to the extent possible. We understand that we're both separated by this computer technology. We can't look at each other's expressions or talk freely with each other, but you can make sure that you can engage with us by asking questions. Make sure you find where that question box is in the control panel, and make sure you take advantage of the downloads. The slides, some of the slides have links that you can use to access some of the materials we're going to be talking about today. And also the reference sheet has a lot of documents that you'll want to add to your water quality library. And as Kristen said, you want to make sure you answer the polls and stay engaged. Keep the webinar tab open. And we might even ask you we might ask some questions like, are we going too fast or too slow? Or do you understand, did I explain the topic adequately? So that would be a good time to use those emojis, like a thumbs up, to let us know how we're doing. Let's jump right in here. This first slide here is representing kind of the scope of our discussion. In a water system, we have a certain point at which we call the entry point to the distribution system. And that is typically after treatment and disinfection, where we enter the distribution system components, which is our pipes and our storage and so forth. If you're in a groundwater system, that entry point you might have multiple entry points after each well, just after disinfection. If you have a system with a treatment plant, you'll have treatment and initial primary disinfection. And after the contact time, it is going to enter into the distribution system. In the distribution system, there are several aspects that we want to pay attention to that are related to quality. For example, in our storage facilities, there are water quality considerations, especially with water age. We could have short circuiting occurring in our storage. Or if we had a storage tank that was designed much larger than we need, we could have excessive water age. Different things can occur in a storage tank, such as nitrification, where nitrifying bacteria consume ammonia in the water and can lead to dangerous levels of nitrate in the water. So those are some of the things that we're going to be discussing. That's one example. We could also have dead ends in our distribution system, where portions of the distribution pipe network that just end and there's not adequate flow. So a variety of things can occur at a dead end. We can lose disinfection residual. We can have high water age. We can have biofilms and bacteria thriving in that dead end if we don't manage it in some way. And in pipes, the topic of pipes in general, we can have bacterial growth, corrosion, and even problems with materials such as leaching and permeation that can happen in pipes. And also there can be points in the system such as sanitary defects and cross connections where contaminants can enter into the system. So that's kind of an example of the things that we're going to be discussing. Now, even though we're talking about this line between treatment and distribution, the source water quality and what happens at treatment, both of those things can have an impact on the water quality in the distribution system. So as we come across those instances, we'll point that out as we're moving through the training. And I hope everyone can hear well, and that you're in the right place and you know what's going on. And if I'm going at the right pace and you can hear me clearly and you can see clearly, you can send us a thumbs up, and Kristen will see that and let us know. One of the topics we're going to be talking about quite a bit is water age management. When water sits in a tank or a process for a long period of time, several things can happen. We can lose disinfection residual, as I already mentioned, as one of the things that can happen. So water age management can include things such as ensuring we have adequate turnover in a storage tank. In a storage tank, we can have short circuiting, or we can have water that remains in the tank too long. We can also ensure that we're periodically flushing dead ends. So those are examples of how we might manage water age. And I believe Daryl's going to talk about this topic a little more tomorrow in more detail. but I wanted to share this graph with you, which is from a resource that is in your resource page. You notice there's a orange line, a blue line, and a green line. And what these represent is some different attempts from studies to model water quality over time. And you notice the blue and the green line, both they're pretty close in agreement. They show a gradual decline in water quality uh, per hour of water age. And surprisingly, in this particular study, only after about 50 hours, the water quality basically goes from great, 100% of its initial quality, down to zero. So you can see the relationship there. And what is included in that performance index there are things like disinfection residual loss, um, heterotrophic bacteria growth, and things of that nature. And you can see that image just below that graph shows things that are happening on the walls of the pipe, things like biofilm growth and corrosion. Those are all associated with water age. And if you look at the different factors that are involved with this topic, uh, loss of the residual, formation of disinfection byproducts, these are things that are more likely to occur the longer your water is held in a tank or pipe. Growth of biofilm, and interactions with pipe scales. Biofilm can interact with pipe scales and cause things to occur such as lead release or increased corrosion, an overall increase of bacteria and pathogenic growth, and increased corrosion and tuberculation, and nitrification in tanks and dead ends. That's nitrification is when nitrifying bacteria consume ammonia in the water and cause nitrate to be released. And if you wanted to take a look at this study, um, I've included the link on this slide. It's called Enhanced Water Age Performance Assessment in Distribution Networks. And so it was done in 2021. It's a pretty recent study, and they were looking at all the factors that can affect water quality. I think that would be an interesting read for you. We're going to go to our first poll already, poll number 1. And it asks, which of the following is a valid method to manage water age in distribution systems? Is the poll able to launch, Kristen?
The poll is launched. And the answer options for this question are: ensure water remains in storage tanks as long as possible, keep at least one hydrant flushing 24 hours a day, periodically flush dead ends, or D, all of the above. And just a reminder, make sure that you get your answers in for these poll questions. This will determine you getting your continuing education credits. And I'll give everyone just a few more seconds. All right, closing the poll right now. All right, Greg, the majority of people said, 82% said C, periodically flush dead ends.
Excellent job. And thank you for managing that, Kristen. I didn't see the poll on my end because I'm on full screen, I guess. And
No
that
problem.
is,
Well, I'll make sure to read through those for each one, okay?
thank you very much. So periodically flushing dead ends is definitely one of the methods we can use to manage water age. So if we have problems with disinfection byproducts, maybe in the warmer summer months, maybe it's a monthly gentle flushing of those known dead ends that we have. We also want to work on preventing contaminants from entering the system. And we're still in the introduction portion of this training here, but there's two general ways that contaminants can enter. One is through cross connections. So a cross connections it's not the same as backflow. Cross connection is a plumbing arrangement that could allow backflow to occur if there was some kind of reversal of flow. So the two types of backflow that could occur through a cross connection is back siphonage is one type where the pressure in our distribution system is lost or reduced. And that could occur because there's a main break or there's excessive fire flow or some kind of outage that reduces the pressure in the distribution system. The other type of backflow is due to back pressure, where we are supplying water to a customer that has some kind of a pressure being applied to the water that exceeds the distribution system pressure. It could be anything ranging from a private well to some kind of boiler or some kind of possibly a chemical process that has a high pressure pump. It could even occur at a car wash, for example. And we try to protect this from occurring by, of course, first eliminating any unnecessary cross connections, but also protecting the water system with backflow devices. And we'll talk about that in a moment. The other general way that contaminants can enter the distribution system is through some kind of sanitary deficiency. It's usually some kind of physical breach in the distribution system that could allow contaminants to enter into the drinking water. And an example could be an unscreened vent in the storage tank where birds or dust or debris could get into the storage tank. And I've seen more than one storage tank that had a bird at the bottom of the tank, and it was sitting in the tank deteriorating and could potentially make people sick. And there's a variety of sanitary deficiencies that could occur. This image here is an example of an air release valve. The whole idea is to release air at high points in the distribution system. And so air should come out and water should not be able to come back in. Now, but if those check valves leak or malfunction, there's potential, if there was flooding or if that pit were to fill with water, there's potential for contaminated water to flow back into the system. And here's another example of a sanitary deficiency. And Daryl's going to talk more about this tomorrow when he goes over sanitary surveys. But here's an example of a improperly sealed well. And you see the discharge pipe and the electrical wire going down to the submersible pump. There's gaps around both of those. So floodwaters and pests can get right directly into the water supply. So cross connections and sanitary deficiencies, we want to manage those and prevent them. Also, another general area is operational practices. This image on the screen, you see some operators that are repairing a water main. They're putting some kind of a joint on the water main, and you notice they're working in a muddy trench with dirty water in it, and that is definitely a source of potential contamination that could get into the system when you're repairing mains. Now, I have two tables I'm going to share with you, and these tables are from that link that is at the bottom right of your screen. US EPA document called New and Repaired Water Mains. That's an excellent document to have in your library. It goes over things that can occur, and it's backed by studies, and it goes through some of the things that you can implement in your operational practices to protect water quality in the distribution system. Now, table 1 here, it talks about 3 categories of issues that can occur associated with either the construction or repair of water mains. So there's microbial issues. Contaminants can obviously enter. You see that trench that hasn't been all the way dewatered with that muddy water, that is very, very likely to have bacterial or pathogenic contamination. Physical issues or things like turbidity. When you see turbidity, in other words, water that has cloudiness or color in it, you can see this water in this trench definitely has color. That means there's particles, and those particles could also contain pathogens. And on the chemical issues as well, you could have potential chemical contamination associated with repair of water mains. If there was any kind of chemical or a nearby sewer main or something like that, you can imagine all of the things that could occur in runoff that have gotten into this trench that could be potential hazards if they entered the drinking water supply. Table 2 here was a study in this document where they looked at some general indicators and if they're present in the trench water. So they found total coliform in 18 out of 31 samples of trench water, so more than half. They found fecal coliform in 12 of 18 samples that they studied. And those two types of bacteria at the bottom, or microbes at the bottom, this Clostridium perfringens and Bacillus subtilis, they also found those in trench water in 9 and 24 incidences, respectively, out of 30 samples. So this represents studies they did just to look at what's in the trench water and what's in the soil. That the column to the right is what's in the soil. So this shows you that when you're working in a trench repairing a main, there's lots of potential um, to have contamination. And those two types of bacteria at the bottom there are bacteria that are associated with different types of waterborne disease. There was, this actually manifested in a serious case in Missouri in 1990. That's not that long ago, but there was 240 cases of people getting sick, documented cases. Or with these kinds of studies, there might be always more that people that got sick, but they didn't go to the hospital. But at least 240 cases of illness, and 4 people died because of an E. coli outbreak, and it was traced back to 2 pipe water main breaks. And when the operators repaired these breaks, they flushed the pipe. They repaired the pipe, got the system going, they flushed it. So they're doing everything right up until that point, but they didn't disinfect the main. And if they had disinfected the main, maybe all these sicknesses and the deaths could have been prevented. Um, so that just shows you the importance of following the procedures all the way through. In general, we want to use sanitary procedures when we repair a water main. And the general steps are to isolate the repair area, flush the main, and disinfect the main. But there's some other factors too involved with sanitary practices. The first would be uh, dewatering the trench, so there's no standing water in the trench that you're repairing, and also disinfecting all the components, the parts, the pipes that you're going to repair, all the tools, um, even your hands, as you're repairing the main. And they recommend to use at least a 1% solution of bleach or chlorine. So you want to disinfect all the pieces. Another aspect that we're going to look at in this training is pathogens. We generally talk about 3 groups or types of pathogens. They can be bacterial pathogens, viruses, or different types of protozoa pathogens. And we also have to deal with biofilm. Biofilm is it's a growth of different types of microorganisms in a film, kind of they call it EPS, uh, this substance, kind of like a gel with this this very diverse group of different types of microorganisms exist together, mainly bacteria, and they can end up kind of protecting, being protected by the biofilm, the pathogens, from disinfection chemicals. And so that it's kind of a complex thing that can develop. And also, you never know when a biofilm is going to release a portion of the bacteria, and it'll enter into the water supply. So, I mean, you could do a coliform test on Wednesday, everything's looking good, and a piece of biofilm could become dislodged and go into, to a drinking water service, and somebody could get sick. It's hard to know. So you want to maintain your disinfection levels and do things such as system flushing, which can reduce these biofilms and help to keep the system clean, so the conditions are not present for bacterial growth to occur, and you're bringing fresh disinfection residual. So we're going to talk about system flushing for a few moments here. And as you probably already know, I know we're preaching to the choir, because a lot of you are experienced operators, but there's several benefits of system flushing. And the top one, it reduces water age, but we mostly do it to remove the portion of the biofilms and scales that are in pipelines and to remove sediments. Flushing can also reduce the formation of disinfection byproducts, and if you flush dead ends, it brings in a new fresh chlorine residual. And another good thing about a flushing program, it gives operators a chance to get around and operate the valves and the hydrants to make sure these are working. Having an operating valve that you can get to, and I've experienced this myself where you need a valve that is been paved over, for example, you don't have access to the valve. And I've also been involved in projects to go and find all those valves and bring them up to grade. And why would that be important for water quality? Well, if you have a main break or some kind of a problem, you want to be able to isolate that section without turning off half the town, basically. But you want to be able to isolate that site to protect water quality, um, and save water, of course, too. And you want to make sure your fire hydrants are working, especially for fire flow um, protection or fire protection, but also for being able to flush your system. So it's good to get around and check these periodically. Flushing once a year gives you an opportunity to exercise the valves, make sure they're working, make sure the hydrants are working. Here's an example of different types of sediments and things that can occur in distribution pipes that can be removed or reduced with flushing. And generally, we want the flushing velocity to be at least 2.5 feet per second, and ideally 5 feet per second. Because we want to attain what's called a scouring action. And there's three different types of material that's represented here that's pretty common. On the left-hand side, you see manganese, which manganese oxide is kind of a black, greasy type of a slime. And, normally water moves very slowly through pipes, and it allows these types of uh, slimes or sediments to build up. And when you increase the velocity during flushing, it can move them out. And so, and in the middle, as you see some iron slime that's being built up, and on the right, you see biofilm being being developed in that pipe. And biofilm is really thin. It might, when we talk about it and show it on diagrams, it seems like it's this real thick layer with all these different types of bacteria and microbial organisms. Well, it does include all that variety of microbial life, but it's actually very thin, like as thin as like a piece of Scotch tape. But to remove these or reduce them, we want to get our velocity up. And when you're opening a hydrant, um, in the first few seconds or a couple minutes, you'll see some dark colors coming out because these things are being removed. Here's an example of flushing using pigs and swabs, and these images here are snippets from an AWWA video, which I'll share the link with you. But a swab is basically it's like a Nerf ball, you could think of, but it's shaped and sized so it fits right into the pipe that you're trying to flush. So a swab is just a big foam projectile, you might say, and a pig is often the same, but it's a little stiffer and has some kind of abrasive quality on the outside normally. But you see on the left-hand side, they're inserting a swab at a hydrant, and then they apply a water uh, pressure source, flow source to push it through the main, and it goes through. It's kind of removing, scouring the slimes and the sediments, and it's pushing it out, and then it comes out at a downstream hydrant or pipe, and it's very effective at removing sediments. You can also have things that are called pigs that are actually data collection devices. For example, ultrasonic pigs, they could measure the thickness of a water main as it passes through very slowly. Those types of pigs, you'd probably run them through just very slowly, but these types of pigs, you're running them through at a pretty good clip because you're trying to remove sediments. And that video it's on your slide at the bottom of that slide there, an AWWA video, which actually animates this process. And here's an image of a couple operators inserting a much larger swab. It looks like it's at least a 24-inch to me. I'm not sure of the exact dimensions, but they're inserting that in, and they're going to run it through a section of main. And you can see a selection here on the far right of your screen of different types of pigs and swabs. The red ones and that middle blue one, you can see there's definitely some abrasive material on the outside that will help to remove some of those slimes. There's also the concept of ice picking. And ice picking is very effective at removing sediments and scales and biofilm. It's often used to remove biofilm. And so ice picking, it uses kind of a semi-solid ice solution. They bring it down to 24 degrees, and it's water and brine that is, it's not just pure water, it's water and brine, because they don't want it to freeze. The brine acts kind of like an antifreeze. It's more kind of like a snow cone. So it has all the abrasiveness of the ice, but it can flow around corners and so forth. You couldn't do that with a solid piece of ice, obviously. Very effective at removing biofilm and sediments. And also you prevent the danger of it getting stuck, because if it somehow were to get stuck, it would just melt. So that's another benefit. And here's a little diagram of the ice pig moving through. You can see in front of it, there's some scales and biofilm on both sides of the pipe represented by those dark areas. And that ice pig is scrubbing those out. Very effective. They have a truck that comes, and they pump the brine solution or the ice pig at an inlet hydrant. And then they open an upstream valve so that will push that ice pig down from the inlet hydrant to the outlet hydrant. And at the outlet hydrant, it'll usually go into a flow analysis unit. And this flow analysis unit allows you to do some testing, especially of the turbidity. So you can look at the range of turbidity that's created when the sediments are moved. And you can see this image here on the right of your screen, all the samples throughout the ice picking process. You see it starts out clean, and then once those sediments and biofilms start to move, it gets pretty dark. And that second bottle, it's really dark, and it slowly cleans up throughout the process until the water is clean. And then they'll usually send it to the sewer to dispose of the flushing water. When you're flushing, you could just open a hydrant, but that wouldn't be very effective. If we just open a hydrant here, there's multiple pathways that the water could flow. So we don't really know which direction it's going to flow, or if it's flowing both directions. So we don't get the velocity that we need. Remember, we want between 2.5 and 5 per second, but if the water is going different directions, we can't attain velocity, and we can't really efficiently move the sediments from point A to point B. We might just be moving the sediments around, but not actually removing them. Instead, what we do is unidirectional flushing, and we close certain valves. Let's say, for example, we want to go down the top pipe and then down the left pipe. We would close particular valves here so that we force the water to go in just one unidirectional path. And then we can be assured that we can attain the velocity we need. And it also helps us to make sure we're thoroughly cleaning each pipe. And we'd go back, and you see there's a middle pipe called P4 and a bottom horizontal pipe called P6 and P3 and P5. We could close different valves to clean each one of those individually. So we can systematically move the sediments, and by flushing the water from the source of the pressure throughout the distribution system one at a time. So we're making sure we're getting all the sediments out. Here's an example of a study, and I've included that study at the bottom of this slide, the efficacy of flushing and chlorination in removing microorganisms. So we have this chart that is from that study, And the chart on the y-axis, it's called log removal. That's how many microorganisms. We're not just talking about sediments here. They're specifically looking at how many microorganisms have been removed uh, compared to the flushing volume. And this is all done at 5 feet per second flushing velocity. But you notice here, it looks at about 3 pipe volumes here gives the most benefit or the bang for your buck. So at 3 pipe volumes, as you increase, you have diminishing returns. Now this log removal, let's say you're looking at 3 log removal, that means you're removing 99.9% of all the pathogens. As you increase in pipe volumes, you're not only wasting water and wasting a lot of electricity and operator time, but you're getting diminishing returns. If you keep on going, they did this study up to 15 pipe volumes. In other words, if the pipe that you're flushing holds 1,000 gallons, you would flush 3,000 gallons through the hydrant. That would be 3 pipe volumes. But they did this study all the way up to 15 pipe volumes, and the returns were diminishing. They weren't getting as much bang for their buck. So the most efficient was 3 pipe volumes at 5 feet per second. If we shift our discussion here to looking at the waterborne disease that's associated with main breaks and repairs here, we can see some fairly recent studies. So one was done in 2007 in Norway. They found that households that were downstream of a main break or repair, that's shocking to me. I can see a main break, but a planned repair is surprising. So anything downstream of a main break or repair, there was a greater incidence of gastrointestinal illness. Same thing in Sweden in 2017, a more recent study. Households were 1.9 times more likely to report an acute gastrointestinal illness after a pipe break or repair in the distribution system. So these are critical tasks that us as operators need to do. Um, we're the ones that have to go out and respond to main breaks and make these repairs. But even planned repairs, they can result and do result in increased illness. So that's why we have to really be careful. There's some factors that we kind of discussed a little bit already, but if you have a wastewater system that's relatively at the same level as the water pipelines, that wastewater main has some, small leaks, we could end up having sewer water in our trench and just contaminated groundwater in the trench just from the surrounding soil, like we saw in the chart earlier. And of course, cross connections. If you have a main break, it can pull in contaminants through cross connections. So you see how all these things are kind of related here. And once again, we want to remember to use those sanitary procedures for repairing main breaks, isolate it, use sanitary repair procedures using that 1% or more solution to disinfect all the tools and parts, and using flushing and disinfection following repair. It's very important. We also may want to issue a boil water notice if we have a loss of pressure. And this image on the right, we see a full circle clamp where a main was repaired here. Depending on the state that you look at, people say this different ways, but if you lose system pressure and the system is compromised, it's a good idea to issue a boil water notice. And if the pressure, that means if the pressure drops even below 20 psi and the system is compromised, you might want to issue a precautionary boil water notice. But for sure, any time that you know that contamination probably has entered. And boil water notice is just letting people know, boil your water before you use it. There's a couple of AWWA standards you might want to have in your library. The first is the C651, which is about disinfecting water mains, and they talk about in that standard about disinfecting water mains after repairs and breaks. And also there's a water main breaks field guide that AWWA offers. But I did put in several resource links into the references sheet about managing water breaks, disinfecting water mains. Now, boil water notice kind of, the length of time that you boil water kind of depends on the elevation. You want to boil it for at least 1 minute, but you might have to boil it longer if you're at a higher elevation. They recommend 3 minutes of boiling for elevations at 6,500 feet or above, because it'll start boiling before it reaches the full temperature. And so after you cool it, then you're able to use it for drinking and cooking and teeth brushing. And after a main is repaired, you would take a back T-test to see if there's coliform present. And after the results come back clean, then you can lift the boil water notice or the boil water advisory. And there's AWWA divides the types of main breaks based on what happens with the pressure. A type 1 break, you're really not losing pressure. It's the water is spraying out through a leak. For example, you go and put a full circle clamp on it, and pressure was maintained during the whole repair. There's no way that contamination could have gotten in that pipe with the pressure at its full level. So you probably would not have to do any disinfection with that type of break. Similar is one that you can maintain pressure, but you do a controlled shutdown, so you're not having contamination. So basically, if you don't lose pressure, you may be able to make the repair without having a specific disinfection process. But anytime you lose pressure, or if the pressure even drops below 20, you then are looking at doing some additional steps, wanting to isolate that possibly, and flush and disinfect, and then disinfect the pipe and all the tools, always with at least a 1% bleach solutions. So the type 3 and the type 4 breaks are different situations where you lose pressure. And the type 4, it's resulting in a widespread depressurization of a large portion of the distribution system. So you might be doing a lot. You might be disinfecting and flushing a lot larger portion of the system than with a type 3 break, where you just flush and disinfect just the portion that you repaired. But in both cases, you've lost pressure. We're going to go to poll 2 now.
All right, that second poll is now launched. How can operators protect water quality when repairing main breaks? A, isolate the repair site using valves. B, flush the line after repair. C, disinfect the main. Or D, all of the above. And then Greg, we did get a question. So someone had asked, are there any concerns with pigging or swabbing causing release of any scales or legacy contaminants? I assume it would not disturb lead service line scales since that is located in service lines, or could that be a concern with ice if a service line is open during the event? And if you'd like to wait and go over this at the end, we can wait as well.
Well, as far as I've looked into this a little bit, and as far as disturbing the like an orthophosphate scale, those types of scales are very hard, and the pigs are not going to touch those. They're going to be moving the things that are softer, like biofilm, and the softer, greasier, manganese and iron deposits. So they're not going to touch the protective scales that are for lead protection.
Wonderful. Thank you, Greg. Go ahead and get your answers in if you haven't already. I'll give everyone just a few more seconds. All right, and I am ending the poll now. Okay, Greg, 100% of people said D, all of the above.
Excellent. You guys are great students. We're going to talk a little bit about corrosion control and cross-connection control here in the next 20 or so minutes here. Now, problems with corrosion. You can see two pipes here that kind of illustrate a really bad corrosion situation that's occurred, and that same pipe, either brand new or with no corrosion occurring. And so one of the things that can happen is tuberculation. Tuberculation is when there's a corrosive force and iron is dissolved into solution, and then the bacteria, iron oxidizing bacteria, oxidize that and deposit it somewhere else. So not only do you have corrosion occurring with the iron being ripped out of the molecular structure, but having it redeposited. And this is a big problem. As you can probably see here, you would have a lot of friction in that pipe. So you're going to have higher energy to force water through those pipes. You're going to have reduced capacity, and you're going to have areas in that pipe that's going to harbor bacterial growth. And of course, eventually the pipe is going to become weaker and weaker and be more likely to break. Also, corrosion is associated with the release of lead and copper. Daryl's going to talk about the lead and copper rule a little more tomorrow, but corrosion is responsible for that, the release of lead and copper. Also, eventually these pipes will leak and you'll have water loss and microbiological problems. The degree of corrosion when you have dissimilar metals connected in either physically or in some kind of electrolyte solution depends on how far they are apart on the galvanic series. And the galvanic series has, it goes from the most reactive to the least reactive. The most reactive on the bottom of the chart, something like magnesium, which is a very reactive metal, up at the top with gold and platinum, very unreactive metals. And electrons will flow from the more reactive anodic metals to more cathodic metals. So if we give an example here, if we have an aluminum fitting attached to a copper pipe, here we have the aluminum and attached to a copper, aluminum is going to be the anode. Electrons are going to be ripped out of that aluminum. Or you can see just above that, the cast iron would also lose electrons to the copper. On the other hand, if we had copper and bronze, copper attached to bronze, so that would make the copper the anode and the bronze would be the cathode. So technically, that would be the relationship. However, these two metals are so close to each other, it's unlikely you would have a corrosion problem between these two types of metals because they're so close to each other on the galvanic series. Here's an example, though, of that iron and copper connection. And this is a very common combination because a lot of times we'll have a copper service line coming from the water main to a home. And if that's a cast iron pipe going to a home, the iron will be the anode and will give up electrons, and the copper will be the cathode. And here's an example of that very thing that occurred. You see a cast iron pipe that had a copper service line, and it was basically destroyed. Now, I say it was destroyed. Now, cast iron, that might have been a 70-year-old pipe or something like that. So, cast iron, it's not our preferred pipe. We don't really install that anymore in water systems. However, a lot of cast iron pipe is still in service, but just know that it is more susceptible to corrosion than something like ductile iron. There was a reason why they made ductile iron and especially cement coated ductile iron, because they're trying to prevent develop materials that are corrosion resistant. The same thing can occur in lead service lines when lead is connected to copper. And here's an example of where a lead gooseneck might be going from the water main to the service line, uh, the lead can prevent, that it will corrode or give up electrons uh, to the copper. And you have this lead release going on, which can result in scale being deposited in the supply pipe and eventually released into the drinking water supply. You can measure corrosion with coupons. And the idea of this is the coupon matches the metal of the pipe or the appurtenance that you're trying to protect. And typically you would have something like a coupon rack that the system water would flow through. And if you look at that coupon rack on the right-hand side, where it says Union style molded holder with CTSBR sample, you notice that's a screwed on cap there that was unscrewed and pulled out to the right, and the coupon's at the end of it. So that's how they would insert the coupon. And you could have several different types. I mean, in this coupon rack, you might have something that is the same metal as the copper pipe that customers have in their homes. You might have a coupon that's the same metal as the cast iron pipe that's in the distribution system and so forth. And so you'd be able to measure it by weighing it at the beginning and running the water through it for a period of time and then reweighing it to see how much you've lost. If you've lost a significant amount of weight, it can mean that you have more significant corrosion going on. There's ways to protect pipes and tanks, and there's 4 categories that I've put these into. There's linings, like this cement lined ductile iron pipe on the upper right of your screen. There's coatings that can be sprayed on the outside of pipes or the insides and outsides of storage tanks. And you see a couple of workers are applying a coating on the inside of a storage tank. Those make physical barriers between the water and the material. Wrapping, here you can see an operator or a construction worker placing a plastic poly wrap around water mains to make a physical barrier between the soil or the groundwater and the outside of the pipe. And it's actually very effective. And then finally, cathodic protection, which uses a DC current. If electrons are trying to flow from the pipe or the tank, the DC current goes in the opposite direction to disrupt that flow, and has sacrificial anodes that will give up electrons instead of the material you're trying to protect. I'll show you an example of that here. On the left-hand side of your screen, you see a cathodic protection of a pipeline, and we have a rectifier that is giving a DC voltage, sending electrons to the pipeline. Now, the corrosion forces would be trying to take electrons from the pipeline, but we're supplying the electrons to the pipeline, and we have sacrificial anodes in near the pipe that are able to give up electrons preferentially. So it's a more reactive metal like a zinc or a magnesium that will give up the electrons that are needed for that corrosive situation instead of the pipe. On the right hand side, you see an image of a storage tank where you have same kind of a concept, but the current flow goes to the anodes that are suspended in the tank in the water, and then the electrons flow, the current flows from the anodes to the tank. So the tank is not giving up any electrons, only the sacrificial anodes. So that's cathodic protection. A way to predict when corrosion is going to occur involves using the chloride to sulfate mass ratio. They call this the CSMR. This was something that is associated with what happened in Flint, Michigan, and I'll show you that in a moment. But basically, you look at the concentration of chloride in your water in milligrams per liter or parts per million, same thing, and you compare that to the concentration of sulfate in milligrams per liter in water, and you basically divide the chloride concentration by the sulfate concentration. So chloride to sulfate mass ratio, CSMR. If that ratio is greater than 0.5, it indicates that the water is likely corrosive. So you see here the formula, CSMR, milligrams per liter of chloride divided by milligrams per liter of sulfate. And I'll give you an example here. We have 10 milligrams per liter of chloride and 22 milligrams per liter of sulfate. If we take 10 divided by 22, that gives us 0.45. So is the water corrosive? Well, because that CSMR is below 0.5, it means it's likely not corrosive. It's considered non-corrosive. This is just one indicator, of course, but it's a good calculation to run if you're exploring corrosivity problems. I'm going to give you a chance to try this here in poll 3. Let's bring up poll 3 and you can check it out.
All right, poll 3 is launched. A water has a chloride concentration of 15 milligrams per liter and a sulfide concentration of 21 milligrams per liter. Is the water likely to be corrosive? And the answer options are yes, no, both, or neither. All right, and the majority of people have put in their polling votes, but I'll give everyone just a couple more seconds and then I'll close the poll. All right, closing the poll now. All right, Greg, so 79%, the majority of people said yes, that the water is likely to be corrosive.
Excellent job, everyone. And let's just look at the solution here. We take the chloride, it's chloride to sulfate, so we take the chloride of 15 milligrams per liter divided by the 21 milligrams per liter of the sulfite, and we get 0.71. And because that's greater than 0.5, it indicates that the water is likely corrosive or potentially corrosive, you might say. There's other factors, such as the Langelier index. If there's a lower pH than the saturation pH, it means that the water is likely to be corrosive. The saturation index or the saturation level means you have a level of alkalinity that is just saturated. In other words, it's not going to be scale forming and it's not going to be corrosive. And so we look at the difference between the actual pH and that saturation level. And this is somewhat depends on the temperature of the water. It's pH dependent. If this is negative, the actual minus the saturation negative, it indicates that water could be corrosive. If it's positive, it means it can be scale forming. If it's 0, it's not going to be scale forming or corrosive. And of course, there's a range. I mean, if there's a large difference between these two, it's likely to be either scale forming or corrosive. If it's real close, it's not going to be as much of an intense effect. But here's an example here. We have an actual pH of 6.8 and a saturation pH of 7.3. And if we were going to predict if the water is scale forming or corrosive, we would take the actual minus the saturation pH. And in this case, we get a negative 0.5, which indicates the water is potentially corrosive. So using the Langelier index along with that chloride to sulfate mass ratio would be, and then of course also looking at the pH and alkalinity and overall water quality, those would be good things to look at. And you could also, the first step if you did have a corrosive water would be to possibly consider adjusting the pH or alkalinity. Alkalinity below 30 is indicative of likelihood to be corrosive. And if you get up higher, even as high as 200 milligrams per liter, it's actually is good to prevent corrosion. Of course, the higher you go, uh, could also be a problem with scale formation if your pH was higher than the saturation pH. If you needed to adjust alkalinity, um, you could add something like lime or soda ash. If you needed to adjust only the pH, you could use something like sodium hydroxide. If those don't work and we need to feed a corrosion inhibitor, we can feed something that results in orthophosphate. And there's several things that we can use: phosphoric acid, zinc orthophosphate, or some kind of potassium-based salt. And if you use phosphoric acid, that's a very dangerous chemical. It can cause severe burns, and so it's not often used. And ultimately, the dosage is pretty low, between 0.5 and 1.5. You don't want it to be too high. You don't want excessive scale to build up. And this orthophosphate, it can even help prevent problems when you transition from one type of disinfectant chemical to another, such as from chlorine to chloramine. In in looking at the different options, no matter what type of chemical you use, it's it's orthophosphate, which is the end result. Um, the PO4, basically, it's a phosphate oxide. Um, so you're trying to create that. So you can use phosphoric acid once again, but more likely you're going to want to use zinc orthophosphate or some kind of potassium-based salt. And you can see some images here on the bottom of your screen. You see that third pipe to the right is actually a lead pipe, but it had a nice coating of orthophosphate on the inside, which was protecting people from release of lead from that pipe. So you can see it was actually working. On the left-hand side of that image, there was uh, a copper pipe there that looks like it might have had some lead particles in the scale, and there was no corrosion control in place for that. And you can see it's pretty deteriorated and was probably allowing lead and copper into the water supply. And you see how it works here. You have, in one, you add the, the chemical, and two, it bonds with the metal at the surface, and three, it captures the lead in the coating, and four, it eventually it reduces the lead levels in the drinking water. Oops. So here's once again, here's tuberculation, and this is an involved uh, process between corrosion and bacteria. You have kind of like a biofilm effect. You have iron bacteria that's basically, it takes that dissolved iron from the corrosion processes and oxidizes it, and it forms a precipitate and continues to form these tubercles, and it can cause a lot of problems. There's a lot of factors that are involved with causing tuberculation. Probably the first one would be just having cast iron pipes, but also you have water, say for example, with a low pH and alkalinity, a higher temperature, and higher water age, and the conditions are right for biofilm growth. Maybe there's a little bit of organics in the water, and then you've got a recipe for tuberculation to happen. And if it does occur, it reduces your capacity, increases the friction, and causes a lot of problems with water quality and main breaks. And scales and biofilms can actually interact in other ways as well, not just in tuberculation. Scales can result when they interact with biofilms, it can result in the release of toxic heavy metals from scales, and the biofilm can take it up, and then as the biofilm detaches and reattaches, it can release some of those. And of course, biofilm can also release pathogens at any time, and it can also enhance corrosion processes because it's occurring near the pipe surface between the biofilm and scale. It's happening at a kind of at a micro level, and it can enhance corrosion. And there was a couple of famous, we already hinted at a couple of these, a couple of famous lead problems that occurred in Flint and DC. DC happened in 2000, and Flint happened in 2014. And these are lessons to the water industry um, that happened. In DC, the water system was trying to comply with the disinfection byproducts rule, and so they wanted to switch from chlorine to chloramines. And but this caused a change in the oxidation reduction potential at the pipe surface, and these lead scales that had developed over years began to dissolve, and it resulted in a lot of lead release. So they had decades of scale that had formed that contained lead in the service lines of people's homes. And it actually was worse as far as the official measured levels than Flint. In DC, they measured levels as high as 80 micrograms per liter. And there was some testing at individual homes that were as high as 308 micrograms per liter, and 100,000 people were exposed. You see the map of DC water. This is a current map showing areas with that still have lead service lines. So they're still dealing with this. They started, they switched to feeding orthophosphate in 2004 as a solution, but this is not a problem that they were able to just solve in in a couple months. It's an ongoing process that they're still working on. But they're in compliance now, but they still have to work on removing the lead service lines. In Flint, they switched a water source from they were taking water from Detroit water, and they switched to the Flint River, and it had variable water quality characteristics, and it had high there was a high chloride to sulfate mass ratio, and they also were using ferric chloride as a coagulant in the treatment process, which except for the problems that occurred, ferric chloride was actually a great choice. It was inexpensive, and it works well in cold weather, and Michigan is a cold place. So, however, adding ferric chloride to water that already had a chloride to sulfate mass ratio problem increased the corrosivity quite a bit. And they had been using Detroit water for 45 years, and they had Detroit water had been feeding uh, orthophosphate. So they had this scale that was in the pipes, the service line pipes, and this scale was dissolved. Kind of the same story, but a different route, and began to release lead and copper. And it was also very corrosive. And so the existing copper and lead service lines were being corroded, and lead and copper, mostly lead was the problem here, was being released into the water. It also uh, resulted in the iron pipes being being corroded, which took away the chlorine residuals. So there was actually some serious problems. Some people died. It wasn't because of lead necessarily. It was because of a loss of chlorine residual, and I think it was 12 people that were affected by uh, by a waterborne disease. They're now in compliance, but there's a lot of factors that these are lessons that we learned here. First of all, that chloride to sulfate mass ratio was 2.04, very high. Um, the corrosivity not only caused problems with lead, but it also consumed chlorine, which reduced the microbial protection. And their lead and copper rule sampling sites, they weren't prioritizing the lead service line locations at that time. So with the data they had, the problem didn't actually seem as bad as it was. So they didn't understand at first the problem. And this resulted in elevated blood levels of lead in children. And the highest official result, the 90th percentile lead result, was 57. Once again, that's lower than what they found in DC. However, there was some independent groups that went and found higher lead levels in some homes and areas. And there's an article on this slide that you can check out. It was evaluating water lead levels during the Flint water crisis. We're going to go to poll 4 now.
All right, poll 4 has been launched. Which of the following actions led to the lead crisis in the DC drinking water system? A switch to a new corrosive water source. B, high chloride due to water quality and treatment chemicals. C, a switch to chloramines as a disinfectant. Or D, lead contamination plume entered the source water. All right, it looks like the majority of people have put in their answers, but I'll give everyone just a couple more seconds to get in any last minute answers. And I am closing the poll now. All right, we got kind of a mixed bag here, but the majority of people said C, a switch to chloramines as a disinfectant. That's 62% of people said that.
Excellent job. And if you're enjoying the training so far, and if I'm explaining things clearly and I'm not going too fast or too slow, you can send us a thumbs up, or if there's a problem, let us know too. You can send us a thumbs down too if you like. Now, if we have a corrosion problem, there's basically 3 categories of options that we have. The most basic would be to simply adjust the pH or alkalinity of the water, more maybe a higher pH or higher alkalinity. We might need to feed some kind of corrosion inhibitor like an orthophosphate. And finally, we might want to replace the materials if we, like if we remove lead service lines and replace it with another material that doesn't leach toxic metals. And there's a document here that you'll want to have in your water quality library. It's the Corrosion Control Evaluation Manual from EPA, and I have the link there. And it takes you through some decision trees that are helpful. Lastly, I'm going to talk a little bit about cross-connection control. And pretty soon we're going to have a little break, and Daryl's going to start with the math. So start in the back of your mind, think about where's that calculator and that scratch pad. Now, we talked about this a little bit already, but cross connections are just simply a plumbing arrangement. And there's 2 types of backflows: back siphonage and back pressure. And a backflow event requires both of these things to be present: the existence of a cross connection and some kind of pressure differential that causes a reversal of flow. There's some different ways to protect against this. And basically, when you put in a backflow protection device, you're removing that cross connection, because the cross connection is a pathway that water can flow through, where if you put a protected device there, water can no longer remove in a reverse direction through that same pathway. A double check valve is an example of a backflow protection device, and it basically is just 2 check valves in series. When the water is moving in the way I have the picture here, if it's moving from left to right, the water pushes those check valves open. It can pass through. If it tries to go from right to left, in other words, a reversal of flow, it forces those check valves closed. And by having 2 valves in series, we have redundancy. And now a reduced pressure zone device, an RPZ device, it's very similar. There's 2 check valves redundant in series. However, it also has a relief valve at the bottom. And if there is a reversal of flow, both those check valves close and the relief valve opens to the atmosphere, so that if there was some kind of a toxic, dangerous fluid in there, it would vent to the atmosphere and it would eliminate itself from the piping. The most positive way to protect the distribution system is by completely separating the system. An air gap would be complete separation. The disadvantage of an air gap is you can't supply pressure to the position. But where we would use it, if we were supplying water to a wastewater treatment plant, for example. We would not want any possible pathway for that wastewater to get back into the distribution system. And the image at the bottom, kind of the bottom left, you show a tank, it's being filled. And if you just imagine that tank has some kind of a dangerous chemical in it, some kind of pesticide or herbicide, we wouldn't want to connect the pipe into the bottom of the tank where it's in contact with the water. If there was a reversal of flow, those chemicals would be drawn back out into the public water system. But even if it doesn't have a dangerous chemical, that tank is not an approved potable water source. And there could be bacteria or pathogens or other types of chemicals that we would not want to get back into the water plant. So we have a air gap, and the distance, the actual gap between the pipe that delivers the water and the tank needs to be at least twice the diameter of the pipe, but not less than 1 inch. So it's completely separating, but you can't supply it with pressure. And the type of device that we use depends on the degree of hazard. So that air gap is the very highest health hazard. We completely separate the systems. Now the reduced pressure zone is the next level. That's for moderate to serious health hazards where you need to have pressure delivered to the system. So you imagine some kind of facility that has a boiler or some kind of a chemical facility where we need to have pressure coming from the system to the plant. We would use that reduced pressure zone. And that example in that image to the right, we have a reduced pressure zone backflow preventer that's going to some kind of a developing lab where there's some chemicals there. We need the pressure, but we have this reduced pressure zone device. There's 2 check valves and a relief valve that give you pretty good protection. And you go down from there, a double check, and then the vacuum breaker is the least. That stops back siphonage. We're going to go to pull 5 now.
All right, poll 5 is launched. Which device provides the minimum necessary protection from backflow when providing water under pressure to a chemical facility? Is it A, reduced pressure zone assembly, B, double check valve, C, vacuum breaker, or D, air gap? All right, the majority of people have put in their answers, but I'll give everyone just a couple more seconds to throw in your answer. And then I'll be closing the poll. All right, closing it now. And Greg, we had quite a variety of answers here. 34% of people said A, reduced pressure zone assembly, and 30% of people said B, double check valve. But both vacuum breaker and air gap also had some answers.
Okay, well, I might not have made that question as clear as it could be, but my intention was to say we have water going to a chemical facility that's potentially dangerous, but we need it to be under pressure, and we wouldn't be able to use an air gap under pressure, but we would probably want to use the reduced zone pressure assembly. There might be cases where we could argue double check valve possibly, but reduced pressure zone assembly would be the highest level that we could protect the water under pressure. And let's look at some of the causes of negative pressure. Thank you for everyone for those answers. I'm going to look at that a little bit more and look at your answers. The causes of negative pressure and back pressure. Siphonage can occur when we have something like a main break or excessive fire flow. And you see an image here where a car has run into one of those Hollywood hydrants. That's the water, the wet barrel hydrants that have water pressure in them, and the car hits it, the water starts spewing out of the main. It creates a low pressure and creates basically a vacuum. And we have at house has at point A has some kind of a tank with a submerged outlet, and it could be a chemical tank. It looks like a bathtub, but it's some kind of tank with a non-potable water supply, and it's being drawn all the way into the distribution system. And notice also, it's going right by a person who's getting a drink at the faucet at that very time. And that could occur on a larger scale. This is a diagram of just one house, but that water passing past uh, someone who's taking a drink at that time could occur in a larger area. Also, elevation differences could cause negative pressure. If we look at some examples here of the same thing, we have a water main break. The pressure is reduced. It creates a vacuum that pulls water through a hose and into the drinking water system. And those green pipes at the very bottom of that image represent other points in the distribution system where that contaminated water could flow if we don't have backflow protection. And basically, this type of a problem could where you have a hose and a bucket is called a submerged outlet. And it could be a plumbing situation where you have a pipe plumbed into the bottom of a tank, or just a hose that is submerged underneath the level. And so any kind of back siphonage can cause that water to be drawn out of that tank. In this case, that image shows some hazardous chemical that the hose is dipped into. One way to prevent that is to have a vacuum breaker, and some communities will require outside hose bibs to have vacuum breakers. And other communities deal with it by making sure that people that apply pesticides and herbicides are educated. But anything that has a submerged outlet needs to be protected with either a vacuum breaker or a vacuum pressure breaker. You can also have a direct plumbing connection where it's going directly from the water right to some kind of a hazardous source, such as a chemical, and that overpressure at the boiler here, or some kind of a back siphonage. Both of those could cause non-potable water from that antifreeze boiler to enter the water main. So a service connection that goes to an industrial process, or if you have a service connection with a customer, a residential customer that has a private well, or a customer that has some kind of high pressure source of liquids or even gases that's connected, and you don't have adequate backflow protection. And here you have an example of the flow of chemicals here from back pressure, from a chemical feeder. And it's going from the chemical feeder all the way through the plumbing to the water main. And you can download that EPA cross connection control manual. The link is on this page at the bottom left. These images are from that. Here's the atmospheric vacuum breaker. It basically vents to atmosphere when it's not in use, or if there's a chance of a backflow. And you can install these. They're commonly installed on outdoor hose bibs. Now the vacuum pressure vacuum breaker, I should say, it's similar, but it's spring loaded, so it doesn't just vent to the atmosphere when it's turned off. It only vents to the atmosphere when there's a potential back siphonage or back pressure. These are commonly used on sprinkler systems. So it's the same kind of a thing, just as a spring-loaded valve. That in other words, the backflow would have to push that spring-loaded valve open for it to close. Some things that you would need for a cross-connection control program: your board would need to make sure that it votes in legal authority to enforce the regulations and find the statutes that support that. You'd want to have a inventory of all the potential cross connections in the system. and training. And you might just, one way to solve that is just to hire an outside contractor that does the backflow testing. And in a lot of cases, water systems require the customers um, to pay for and contract the backflow testing service. But you need some kind of way to keep records too, because each year, at least annually, all of the cross connection control backflow devices should be inspected, and it should be reported to the utility. You need to have a record of that. And I've included a couple of resources that you could check out on this slide. Plumbing code link, the Association of Plumbing and Mechanical Officials link, and a set of standards from that international association. And the goals are obviously to prevent harmful substances from entering the drinking water, but also identifying and eliminating any cross connections and sanitary deficiencies. And you want to establish some kind of a uniform set of standards that protect water quality throughout the distribution system, and require businesses and industries and residences to install the appropriate type of backflow device. So you want to know the answer before the question comes up of what kind of backflow device is needed. And we're going to do poll 6 now, and this is our last poll before I turn it over to Daryl. And I'm a little behind, Daryl. Sorry about that. But go ahead, Kristen, and I'm going to be bowing out as soon as this poll is answered.
All right, sounds good. We'll pass it over to Daryl once this poll is finished. What type of condition would cause contaminated water to flow into the water system through a submerged outlet? A, low or vacuum pressure in the distribution system. B, high pressure in the customer plumbing. C, excessive distribution system pressure. Or D, all of the above.
So Kristen, how about we just we take 10 minutes from this point? We'll get our break in, and I'll cover the poll question and when we get back.
That sounds good. The majority of people have put in their answers, but we'll give everyone just a couple more seconds and then I'll close the poll. We'll take a quick break and then we can switch things over to Daryl. All right, I'm closing the poll now. And Greg, did you want me to go over these answers with you or just wait for Daryl?
It sounds like Daryl's going to cover it, so that's
okay.
That's
yeah.
fine.
All right.
I'll just stop sharing and let Daryl bring up. Thank you, everyone. Thank you for being a great audience.
Thanks, Greg.
Oops, I accidentally revealed it.
right, we're going to give everyone just 2 more minutes. 2 more minutes. So use the bathroom, grab some water, do what you got to do, and then we'll get this training back started. All right, Daryl. I think we can go ahead and get started.
All right. So poll 6, what type of condition would cause contaminated water to flow into the water system through a submerged outlet? Example, a hose in a chemical bucket. A, low or vacuum pressure in the distribution system. B, high pressure in the customer plumbing. C, excessive distribution system pressure. Or D, all of the above. Kristen, can you tell us how the responses came out?
Yes, so the majority of people said A.
Okay, and A is the correct answer. So if you remember back to the examples that Greg used, this would have been the submerged outlet example. And that's, quite often that, the bucket in the, on the hose bib outside someone's home or something like that. All right, so I'm going to get started on basic distribution system math concepts. So in the next half hour or so, we're going to cover volume calculations, flow, pressure, concentration, and dosages. The first of these we're going to look at is rectangular volume. The volumes can come into play if we're talking about, in this, for rectangles, it's often tanks. So the volume of that would be the length times the width times the height. And in this example, we've got a 4-foot wide tank. It's 4-foot long tank, 2-foot wide tank, and it's 3 feet in height. And so our volume would be 24 cubic feet. Note that FT to the third power is an abbreviation for cubic feet. So the more common one would be our cylindrical volumes, and that's quite often our tanks and our water main or pipes. And the formula for that, there's a couple different ways we can do this. One of them is 0.785 times the diameter times the height. And I think that like the one that I learned would be pi times r squared, the radius, times the height. You can use either one of those formulas. And we've got a little example here. What is the volume of a tank with a diameter of 20 feet and a height of 30 feet? So we can put that information into either formula. In this case, the 0.785 times the diameter of 20 times the diameter of 20 times the height of 30. You could also use pi r squared, in which case you're going to use the radius of 10 instead. And that gives you 9,420 cubic feet. If we want to know what that's in gallons, we're going to have to take the number of cubic feet, and we're going to multiply it by this conversion factor of 7.48 gallons per cubic feet. And that tank with a diameter of 20 feet and height of 30 feet would have 70,461.6 gallons in it. So we had mentioned that, I had mentioned just previously that there's a conversion factor, and what we're saying is that 1 cubic foot of water is equal to 7.48 gallons. It's almost 7.5 gallons. So here's a quick question. So how many gallons can a 24 cubic foot tank hold? So if we take our 24 cubic feet, we multiply it by the 7.48 gallons per cubic feet. The cubic feet are going to cancel. We'll have left over a number that's in gallons. And so in a 24 cubic foot tank, we'll have 179.5 gallons. All right, so let's look at some volume conversions. So a gallon of water is also equal to 231 cubic inches. So how many cubic inches are in a cubic foot? We simply take and multiply each of those sides together, 12 by 12 by 12. And so there's 1,728 cubic inches in a cubic foot. So then that begs the question, how many gallons are in that cubic feet, or that 1,728 cubic inches? So if we take our 1,728 cubic inches, we divide it by the 231 cubic inches in 1 gallon, our cubic inches will cancel here, and we'll be left with 7.48 gallons is equal to a cubic foot. So we've kind of come around in a different way to show that conversion factor, where it comes from. And that's probably something that if you're in the water industry, that's a conversion factor that's worth memorizing. And it may become helpful in our poll questions as well. Speaking of poll questions, we're at our first one already. We have a cylindrical storage tank with a diameter of 24 feet, and it's filled to a height of 20 feet. How many gallons are in the tank?
All right, Daryl, the poll is launched.
This group seems to be pretty quick in their responses, but sometimes the math makes it take a little bit longer.
Mm-hmm. Yeah, luckily I can see the percentage of people that have voted, and so I will not close until most people have put in their votes. All right, get in your answers. Most people have now voted. I'll also say if you do end up getting any of these questions wrong, that will not prevent you from getting your continuing education credits. These are learning checks to make sure that you are here with us and you are actively participating. All right, closing the poll in 3, 2, 1. All right, Daryl, so 55%, the majority of people said C, 67,643 gallons, but quite a few people, 32%, also said A, 9,600 gallons.
Okay, thank you. So the correct answer is 67,643 gallons, C, and we will go over how we come up with that answer here. So if we take our formula for the volume of a tank like this, we take 0.785, we multiply that by the diameter of 24 feet times the diameter again, and then multiply by the height of 20 feet. And then ultimately we need to convert cubic feet to gallons, so we multiply by 7.48 gallons per cubic feet. We put those numbers in, we get 67,643 gallons. All right. So if you're interested in what this relationship, why we can use 0.785 instead of at times the diameter squared times the height instead of the pi r squared times the height, it's because there's the relationship between 0.785 and pi. So pi is the ratio of the circumference of a circle to the diameter. It's an irrational number. It goes on forever. Typically, we shorten it down to 3.14 for most of our uses, and most of the time we do calculations. And that traditional formula is for an area is equal to pi r squared. When you use the diameter instead of the radius, you're going to use the radius is equal to the diameter divided by 2. So if we put that in there, as you can see, when we work through this formula, 3.14 times the diameter divided by 2 times the diameter divided by 2. The dividing by 2 comes out as a 4 on the bottom. And that ends up being, we divide 3.14 by 4, it becomes 0.785. And so that's how that relationship works. So what we're saying is that the area of a circle, a square with sides the same as the diameter, we're at about 78.5% of it. And that's kind of depicted here in this figure over on the right. Yeah, if Ingrid moves me out of the way. So that just shows you the relationship. And more and more the 0.785 is becoming, I think it's simpler for some people. So I think that's why we're starting to see it used. But you can use either one, whatever works for you. So now we're going to go on to talk about flow. And flow is quite often depicted as Q. And flow is the area times the velocity. Some of the units we'll see flow in, cubic feet per second, gallons per minute, gallons per day, million gallons per day. Our area for this formula is quite often in square feet, velocity in feet per second. So if we're looking at, we need to determine the area of a circle. In this case, if we're looking at the cross-sectional area of pipe flow, we're going to use our 0.785 times d squared or pi r squared. So what is the area of a circle with a diameter of 4 feet? Should just simply put that into either of our formulas. 0.785 times 4 times 4 gives us 12.56 square feet. So now we've got a little bit of an example problem here. Water is moving through a 6-inch pipe at a velocity of 2 feet per second. What is the flow in cubic feet per second? So the first thing we're going to do is we're going to convert from inches to feet. So we've got our pipe diameter is 6 inches. We want to get that into feet. So we've got similar units and we can run our calculations. So if we divide the 6 inches by 12 inches, that'll tell us that we have a half a foot as a diameter. Next thing we want to do is we want to calculate the area of our pipe. So the area is equal to 0.785 times 0.5 times 0.5, or it's 0.19625 square feet. So that's the area of our 6-inch pipe in feet. Now we're going to use the flow formula. So we know our area and we know our velocity. They gave us a velocity of 2 feet per second. So we're going to put those in. So Q equals our area times our velocity. In this case, 0.19625 square feet times the 2 feet per second. The result is going to be that our feet are going to go from, we've got squared and we've got a single, so that'll be cubic, and we'll have 0.3925 cubic feet per second. So that's the flow of our in a 6-inch pipe with a velocity of 2 feet per second. So let's look a little more at this equation. So we can modify this equation if we look at it and we divide both sides of the equation by A. So what we're going to do is we'll have Q over A on one side, and if we divide both sides of the equation, we're going to cancel out the A's on the other side. So that in essence is going to give us our velocity is equal to flow divided by area. And this is helpful if we know what our flow is and we can calculate the area of our pipe, then we can determine what the velocity is in that pipe at that flow. So let's look at a pipe with a cross-sectional area of 0.23 square feet. It has a flow of 0.75 cubic feet per second. What is the velocity in the pipe? So if we take our velocity is equal to the flow, 0.75 cubic feet per second, we divide that by the area that they gave us of 0.23 square feet, we'll get a velocity of 3.26 feet per second. All right, we're on to our poll number 8. What flow in gallons per minute is needed to flush a 500-foot section of 6-inch water main at a velocity of 5 feet per second?
All right, Daryl, that poll is launched. Looks like we have just over 50% of people that have put in their answers, so I'm going to give everyone some more time. All right. Majority of people have now voted, and I'm going to be closing the poll in just a couple of questions, so make sure that you get, or just a couple of seconds, so make sure you get your answers in. All right, closing the poll now. And Daryl, we had 45% of people said B, 440.4 GPM. And 36% of people said C, 98.1 GPM.
So it's pretty close. All right. So our answer is B, 440.4 gallons per minute. How do we come up with that answer? Okay, so we're going to use that area times velocity is equal to flow equation. So our pipe area to start with is 0.785 times the diameter times the diameter. So that's 0.785 times 5 feet times 0.5 feet times 0.5 feet. So our 6-inch pipe, we're converted that into feet. So it's a half a foot. So we've got that 0.19625 square feet. So the next step is to multiply that area by the velocity that they gave us. So the area 0.19625 square feet multiplied by the 5 feet per second gives us 0.98125 cubic feet per second. All right, so then we have to convert. We got to go from cubic feet per second to gallons per minute. So in order to do that, we're going to take our 0.98125 cubic feet per second. We're going to multiply by 60 seconds in a minute. So that will cancel out our seconds. And intermediately, we would have cubic feet per minute. And then we're going to multiply by the number of gallons in a cubic feet. That's 7.48 gallons per cubic feet. That cancels out our cubic feet and gives us a resulting answer in gallons per minute. And that is 440.4 gallons per minute. So this whole idea of the flow rate in gallons per minute. So we've got a tank. It's a 5,000 gallon tank, and we've got a pump connected to this, and it takes 12 minutes for that pump to fill that tank. So what is our output in gallons per minute of our pump? If we simply take the 5,000 gallons, we divide it by the number of minutes that it takes, we'll get 416.7 gallons per minute. Now, if this same pump ran for an entire day, how much water would it pump? Okay, so if it does 416.7 gallons in a minute, we're going to have to figure out how many minutes there are in a day, and we'll do that calculation. You'll note that if we multiply our gallons per minute by minutes per hour, we're going to cancel out our minutes. And if we multiply that by the 24 hours there are in a day, we will get rid of our hours, and we'll be left with an answer that's in gallons per day. So that same pump would pump just over 600,000 gallons in one day. So if you so choose, if you like to memorize these different conversions, there's one here you could use. Just tells you the number of minutes basically in a day. I personally will probably write mine out. I like to see my numbers cancel out so that and then have to memorize fewer things. All right, so we can looking at flow rate and conversions from gallons per minute to million gallons a day. If we take that, our gallons per minute, we multiply that by the number of minutes in a day, that 1440 that we calculated. You could also do, minutes as we did before, 60 minutes in an hour, 24 hours in a day, multiply that out, it's the same. And then we divide that by 1 million gallons per this M gallon, and that's just a placeholder for the M in the MGD. So a pump produces 400 gallons per minute. What is its flow in MGD? So if we take our 400 gallons a minute, we multiply that by the number of minutes in a day, 1440, and we divide that by 1 million gallons per the M gallon, which is the million gallons per the M gallon is essentially dividing it by 1. So we do that, we'll end up with 0.576 MGD. So our gallons cancel out, our minutes cancel out, and where the M gallon in the denominator and the denominator of the denominator ends up on the top, and then it's per day because that denominator still stays. So we end up with 0.576 MGD. So we can do flow rate conversions between CFS and GPM, and from GPM to CFS. And so what we're going to utilize to do it from CFS to GPM is we're going to take the cubic feet per second, whatever we're given, multiply by that 60 seconds per minute, and then by 7.48 gallons per cubic feet to give us gallons per minute. So the seconds will cancel, the cubic feet will cancel, and we'll end up with something in gallons per minute. Now, if we want to go in the other direction from gallons per minute to cubic feet per second, we're going to take what we're given in gallons per minute, multiply by 1 minute per 60 seconds, and then multiply by 1 cubic foot per 7.48 gallons. And so our gallons will cancel, our minutes will cancel, and we'll be left with something in cubic feet per second. So we've got an example of a pipe that has a flow of 0.5 cubic feet per second. What is this flow in gallons per minute? So we take our 0.5 cubic feet per second, we multiply it by the 60 seconds in a minute, and 7.48 gallons per cubic foot, which is this top formula, we end up with 224.4 gallons per minute. So now we're going to look at going in the other direction. If we've got a pipe that has a flow of 500 gallons per minute, what is that flow in cubic feet per second? So we have our 500 gallons per minute times 1 minute per 60 seconds times 1 cubic foot per 7.48 gallons. Gallons and minutes cancel out, and we end up with 1.11 cubic feet per second. So now let's look at a problem or a situation where we have flow velocity and we're going to do a conversion. So we've got a pipe and it's got a diameter of 18 inches and it's got a flow of 800 gallons per minute. What is the velocity of flow in the pipe? First step, we want to get everything into feet. So we need to take that 18 inches and convert it into feet. We simply divide 18 by 12, and that tells us that we have that 18-inch pipe is 1.5 foot in feet. Next, we're going to calculate our area. So we take 0.785, we multiply by 1.5 and by 1.5. Remember, you could also do pi r squared. Either one works, and that answer is 1.766 square feet. And then our third step is we're going to determine the flow. So we're taking our 800 gallons per minute, multiplying by 1 minute per 60 seconds, then multiply by 1 cubic foot per 7.48 gallons. We do that, our minutes and our gallons cancel out, and we're left with an answer in CFS, or cubic feet per second. That's 1.783 cubic feet per second. So now we go back to that to where our formula where our velocity is equal to our flow divided by the area, because we want to know what the velocity is in the pipe. And so we take our flow of 1.783 cubic feet per second, we divide that by the area of 1.766 square feet, and 2 of the square feet will cancel out. We'll be left with feet per second, which is a velocity, and it's 1.01 feet per second. All right, so we're on to poll number 9. Water is flowing in an 8-inch diameter main at a velocity of 1.5 feet per second. What is this flow in MGD? Select the closest option.
Thank you, Daryl, and that poll is launched. And although I couldn't put it in the question in this poll, he did say select the closest option. right, the majority of people have their answers in, but I'll give everyone just a couple more seconds. All right, closing the poll in 3, 2, 1. All right, Daryl, so the majority of people, 60%, said C, 0.34 mgd.
All right, well, that's great, considering the answer is C, 0.34 mgd. And we will go through the solution for that. So we've got water flowing in an 8-inch diameter main at a velocity of 1.5 foot per second. What is the flow in mgd? So we look at our flow is going to be equal to the area times velocity. The diameter of our pipe, converting that from inches to feet, we divide by 8 inches by 12. That gives us 0.667 feet. And we put it into our area calculation, 0.785 times 0.667 times 0.667 gives us 0.349 square feet. Okay, so we need to then determine what that flow is in what the flow is in cubic feet per second. So we take our flow is equal to our area times our velocity, and this, so that's 0.349 square feet times 1.5 feet per second. We end up with cubic feet per second, and it's 0.5235. Next thing we want to do is convert that from cubic feet per second to gallons per minute. And when we do that, you can see that we need to convert from seconds to minutes. So there's 60 seconds per minute. The seconds cancel out. And then we also have to multiply by 7.48 gallons per cubic feet to get it into gallons and out of cubic feet. And that cubic feet cancel. It gives us 234.9 gallons per minute. Now, if we need to convert from gallons per minute into million gallons a day. So we multiply the gallons per minute by the number of minutes in a day and divide by that 1 million gallon per mg. And that gives us 0.338 mgd. And so the closest answer to that is 0.34. We round that up. And there's a lot of variations that people can use in these, how many decimals they take that out. That's why chances are you're not going to get the same answer. That's why we say, you know, it should be close, you know, pick the closest answer. So now we're going to talk about pressure. And so pressure is the force that water exerts over a unit area. We express pressure in pounds per square inch or pounds per square foot. And we know that water weighs 8.34 pounds per gallon. There's another factor that as water people we should memorize. And we know that the 7.48 gallons per cubic feet. And if we multiply those two together, the gallons cancel out and we end up in pounds per cubic feet. So we know that water weighs 62.4 pounds per cubic foot. So if we want to look at an example of a PSI conversion, pounds per square inch, we take 1 square foot is equal to 12 inches times 12 inches, or 144 square inches. And if we know that there's 62.4 pounds per square foot, and we multiply that by 1 square foot per 144 square inches, that tells us that there's 0.433 psi for every foot of water. So that's another thing that's probably worth memorizing, that there's 0.433 psi for every foot of water. Now, if a foot of water is 0.433 psi, we can divide a foot by 0.433, and that'll tell us that there's 2.31 feet for every psi. So there's another important 2.31 feet per psi is another important thing to remember. So pressure example. So in this example, we're going to look at, we've got a 10-foot wide by 20 foot long by 6 foot deep tank. And we've already calculated out, and that holds 8,967 gallons of water when it's full. The water weight, if we take that 8,976 gallons, we multiply that by 8.34 pounds per gallon, we know that that water weighs 74,850 pounds. And all of that acts on that 10 by 20 foot bottom of the tank. So what is the pressure in PSI on the bottom of the tank? So the first thing we want to do is we're going to calculate the pressure in pounds per square feet. So we've got 6 foot of water. Got 6 foot of water, and we know that it weighs 62.4 pounds per cubic foot. So that means we have 375 pounds per square foot. Now, if we want to convert that to PSI, we know that a square foot is equal to 12 inches by 12 inches, or 144 square inches. Pressure in PSI is going to be that 375 pounds per square foot multiplied by the 1 square foot per 144 square inches, or it's 2.6 pounds per square inch, or 2.6 PSI. So that's what our pressure is in PSI. We note that the pounds cancel, or the pounds stay, the square feet cancel, and the square inches stay. So pressure can also be looked at a little differently here. So pressure is pounds per square inch, or PSI. So we said that 2.31 feet is equal to 1 PSI. So that's so every 2.31 foot of water column adds 1 PSI of static pressure. So what is the pressure at the bottom of a standpipe filled to the 40-foot level? So we've got the standpipe. We want to know what the pressure is here at the bottom. So we're going to take that 40 foot of height, and we're going to multiply that by 1 PSI per 2.31 feet. Those are equal, so we can multiply them by each other. Note that the feet are going to cancel, and that's going to give us an answer in PSI. So a 40-foot high water column is going to have 17.3 PSI. So our next pole, we have a standpipe with a 25-foot diameter. It's filled to a level producing 11 PSI at the tank bottom. How many gallons are in the standpipe?
All right, Daryl, that poll is launched. Just about half people have put in their answers, so I'll give everyone just a little bit more time. All right, if you have not already, go ahead and get your answers in. I'll be closing the poll in just a couple seconds. All right, closing the poll now. All right, Daryl, so the majority of people at 46% said B, 93,214.8 gallons. But quite a few people also said C, 73,173.6 gallons.
Okay, thank you. Yeah, so the answer is C, 73,173.6 gallons. And I understand that this is not a lot of time to respond to these math questions. I apologize for that. Given the time that we have to move along pretty quickly. So we'll look at the solution to this. So we've got our storage tank. It's filled to 25 feet. There's a pressure of 11 psi at the bottom. How many gallons are in the water in the standpipe? So the height of the water column, if there's 11 psi, we know there's 2.31 feet per psi. That means we have a height of 25.4 feet. The first thing is we're going to determine, we needed to know how high that was. So then we're going to look at what's the volume of the tank. If we've got a tank that's 25, it's got a diameter of 25 feet and it's got 25.4 feet of water in it, we multiply 0.785 times 25 times 25 times the 25.4, the height, and then we'll convert from gallons to cubic, or from cubic feet to gallons by multiplying by 7.48 gallons per cubic foot. That gives us 93,214.8 gallons. Whoops. So that's how we came up with that answer. Fortunately, there's only one more math poll question. Now we're going to look at concentration, just the concept that the different ways that we can look at concentration. We can look at parts per million. Parts per million is simply the number of parts of something over a million parts. And when we look at milligrams per liter, it's pretty much the same thing, because there's a million milligrams in a liter. So what we're doing is we're comparing the number of milligrams to a liter, but it's really the number of milligrams per million milligrams. So those are the same, and parts per million and milligrams per liter are the same thing. It's an important, I'll use them interchangeably, and it's important to understand that they're the same. I think that causes a lot of confusion. We also look at concentration in percentages. We are all accustomed to, what a percent is. 1 out of 100 is expressed as 1%. Well, if we're looking at milligrams per liter, 10,000 milligrams per liter is equivalent to 1%. And then, doing the conversion between 1 divided by 100 is being equal to the fraction, or to 0.01 as a decimal. The last, I don't know why this shows up the way it did here. The last idea that we're going to cover is the pounds formula. It's the idea that we're taking our flow in million gallons a day, we're multiplying by the concentration in milligrams per liter, or parts per million, however you want to look at it. And then we multiply by 8.34 pounds, and that's going to give us our feed rate in pounds per day. So we have a well that produces a flow of 600 gallons per minute. All right, so we already know we need it in million gallons a day, so we're going to have to change that. And then the chlorine dose is 1.5 parts per million. All right, what is the feed rate of gas chlorine in pounds per day? So gas chlorine is 100% available, so we will first convert our flow to million gallons a day from gallons per minute. To do that, we take our 600 gallons per minute, we multiply by the number of minutes in a day, and then we divide by that 1 million gallon per mg. So that's going to tell us that we have 0.864 mgd. That's our flow when we convert it. So now we're going to use our pounds formula. This formula up here, we're going to take our flow in mgd. We're going to multiply that by the concentration in milligrams per liter or parts per million, and then we'll multiply by 8.34 pounds per gallon. And we get an end result of 10.8 pounds per day. So we can look at another example to help understand this. A water well flows at 1.2 mgd and has gas chlorine dosed at 2 parts per million. What is the feed rate in pounds per day? We take our 1.2 MGD, our flow, we multiply that by the parts per million, 2 milligrams per liter, and then we multiply by the weight of a gallon of water, and that at 8.34 pounds per gallon, and that gives us 20 pounds per day. If we rewrite the formula, we can look at this as as 1,200,000 gallons multiplied by 2 parts of chlorine per 1,000 parts, and then multiplied by 8.34 pounds per gallon. And you can see that we're gonna cancel out a lot of these digits as we go through. So how much does 1,200,000 gallons of water weigh? If we simply take this part of the equation and that, we multiply that together, we know that there's over 10 million pounds in 1,200,000 gallons of water, or 200,000 gallons of water. So if we take that 10,008,000 pounds, and we multiply that by the 2 parts of chlorine, we once again, it's just another way to get to our 20 pounds per day. We divide by our million parts. This helps shows that the concentration in pounds formula expresses the weight of chemicals as a portion of the weight of water. In this case, chlorine weighs 2 out of 1,000,000 times the water weight. All right, so we're on to our final poll. A groundwater well produces a flow of 350 gallons a minute. Chlorine is dosed at 1.3 parts per million. What is the feed rate of gas chlorine in pounds per day?
Thank you, Daryl, and that poll is launched. All right, the majority of people have their answers in, but I'll give everyone just a couple more seconds to get those answers in if you haven't already. All right, closing the poll in 3, 2, 1. All right, Daryl, so the majority of people at 68% said C, 5.46 pounds per day.
All right, thank you, Kristen. And the majority of people are correct. So the answer is 5.46 pounds per day. So let's look at how we came up with that. So we've got a well that produces 350 gallons per minute. Chlorine dose is 1.3 parts per million. What's the feed rate in pounds per day? So the first thing that I would do is convert the flow to MGD from gallons per minute. We do that by multiplying the gallons per minute by the number of minutes in a day. And we get 0.504 MGD. Okay, so we know what our flow is in MGD. Our next step is to take and use our pounds formula, where we take that flow in MGD, multiply it by the concentration of 1.3 parts per million, multiply by 8.34 pounds per gallon, and we get 5.46 pounds per day. All right, good stuff. So what did we cover today? We did a water quality overview. We talked about system flushing, some corrosion control, cross-connection control, and then I talked about some basic distribution system math ideas. So main takeaways, typically people can only focus on a few things, and what do we want you to know? Flushing, water age management is most effective at a velocity of 5 feet per second for 3 pipe volumes and is part of water main repair procedures. Water age control and biofilm management to improve water quality. Corrosion control, it involves knowledge of water quality factors and can require adjustment of pH and alkalinity or orthophosphate treatment. Cross-connection control involves protecting public health by ensuring adequate separation or isolation between contaminants and drinking water. All right, so we appreciate everybody for being here today. If you want to share something that you enjoyed learning about in the chat, we'd appreciate that. And then we've got about 5 minutes before this is officially done. We're open for questions.
Thank you, Daryl. And I did want to mention, someone did note that for poll 10, not the last question, but the question before, the answer that was circled was actually the incorrect answer. The correct answer was the 93,000, which you had noted, but it was just circled as C, which was 73,000. Just wanted to make note.
We will have to make a correction. Thank you for
yes.
up.
And I see, let's see, I see a raised hand here. I know we had a question come in earlier when Greg was presenting, and the question is, how do you measure corrosion potential for groundwater supply?
Is that for, do you have any input on that, Daryl? I don't have a good answer except for, the measurements that we talked about, the LSI, the Langelier index, combined with the chloride to sulfate mass ratio, combined with a kind of an intensive water quality analysis of pH and alkalinity, and maybe using coupons. There's laboratory tests that are done and like pilot studies to determine it. There's not really a simple, unfortunately, there's not really a simple calculation that you can do to measure corrosion potential, and it depends on the type of the metal, and it's very complex, and it requires a pilot study, as far as I know. If you have any additional information on that, Daryl, I'd be happy to.
I don't think I could comment on that beyond what you've already said, Greg.
I've searched for the same thing. What's the end result? How can we do a simple calculation and have corrosion potential? But as far as I know, nothing like that exists. I think it's a combination of factors. But it's a good question. It's a good question.
Thank you, Greg. And we have not received any other questions, but if anyone does have a question, go ahead and type it into the question box. You can also raise your hand and I should be able to unmute you as well. And I see a question regarding if folks need to include their EPA number for contact hours. As long as you included your ID whenever you registered, then we have that information that we need. So whenever we submit you for continuing education credits, we should be all set. If you do not remember putting in your ID, that's something that you can just plug into the questions or comments in the feedback survey, which will be sent after you close out of this webinar. And we'll be sure that that information is included. All right. I see no further questions, so I guess we can go ahead and close out for today. A huge thank you to Daryl and Greg for sharing their expertise with us. Following today's training, you'll receive a follow-up email with a link to the recording, and we ask that you please complete the evaluation. Thank you again, and we hope to see each of you at tomorrow's part 2 of this virtual workshop.
Thank you,
Thanks,
Kristen.
Daryl. Thanks, Greg.
Thanks,
Have a
Greg.
great day.
Thank you, everyone.